This is video help from problem 12.1. Again, see the written homework hints. There's some things there that I'm not going to repeat. I want to try to understand things as well as possible to help us as we get started. Two keys that I probably want to emphasize here. First key, if we sample k values discretely, every step delta k, not continuously. Remember, delta k then would be some, delta t if I'm going in the read direction. We then have a Fourier series, really, not a continuous Fourier inverse transform. In fact, you can find in the chapter the inverse Fourier transform, not exactly the row, so it's a reconstructed row, so we call it row hat. This will be then a sum. It's, you can think about like the integral is discretized. And so our dk just goes to finite steps delta k and evaluated at the finite steps, p delta k. P is an integer. And e to the ip, and this is kx, where k is p delta k. I'm going discretely in k. Well, this exponential is invariant. It's periodic. If I replace x by x plus 1 over delta k, if 1 over delta k here cancels this, and then I just get 1, that shows you this is periodic in x. And that's what happens for any Fourier series. There's some fundamental period or, k step. And in this case, then, that it translates into 1 over delta k periodicity in x, and that's why we call that L, the field of view. We are periodic over this because when we make a measurement, when we look over L, we're not going to get anything different when we go over next L and multiples of L. Just looking at one L, and that's it. Well, there's no big deal if when I look at some object that has some distance a, let's look at a boxcar, then my reconstructed image will be, if the field of view is greater than a, it'll get repeated indeed, but who cares? Because all I want to do is just look at this one, look at one of these. And in fact, then I would be just looking at this row hat over some field of view L. But if L is less than a, that's the aliasing story. That means to you that if I look at sort of the fundamental boxcar here, I know that when I go a distance L less than a, I got to repeat. If I go at L less than a, I repeat. I keep repeating this. Say like the left edge appears at a distance smaller than the size of the boxcar. It's aliased. So I have to, this will be periodic, this will have to be periodic. And what it really says to you is that delta k in this sense is too big. So that 1 over delta k is too small. Our steps are too big. If you make real tiny steps, then you won't have this problem. Now the second thing is, we're going to assume the receiver coil covers this whole guy. I've got a big coil outside here, and I pick up all the signals from all the protons making up this sample. Well, if that's the case, then I gotta realize that when I integrate my whatever I've got for rho dx, that's the number of spins, and I better have exactly the same thing. And you can just prove it by looking at the formulas that I'm going to talk about in a second. But the number of spins must be the same. Well, we originally had a profile like this for rho dx, but that's not what we have up here. We've got some rho hat. In fact, if I go, let's look down here. Let's look at just a centered field of view. It's less than a. Then I know that I'm going to actually have in this center view, I'm going to have some part of the ghost of the next boxcar overlapping it. Similarly on this side, part of the boxcar overlapping this thing. Remember, when I go from any point of this boxcar to point of this boxcar, it's going to be the exact same point on the boxcar here. It's going to be L less than A. But you know, I got to have this area the same. And sure enough, that helps you understand why, well, I've actually got an overlap here. I've got double numbers of proton spins here and double numbers of proton spins here, so that this is going to pile up to be bigger, and it's going to look like this, and that area is going to equal that area. And that's aliasing, and this is what I'm going to see, and I'm going to not see a boxcar, I'm going to see a castle, or whatever you want to call that. Mathematically, by the way, we have some formulas also in chapter 28, that the signal we see, which will be aliased because of this periodicity, will just be the sum of all of the signals that overlap in a region. So we're going to look in here, minus L over 2 less than X less than L over 2. But in that region, some of the S that's been translated will overlap on this because L is less than A. And therefore, you're going to see pictures like this, and you can look at the written things for some more quantitative statements. Finally, let me just mention, if I had a human body, I got a torso, I got a left arm, I got a right arm, and if this is aliased, such that I don't have a torso over here, I've got it overlapping, I'm going to have something like the left arm here and the torso and the right arm here. I'm going to have, and let's suppose my field of view is just really the torso, I'm going to find a left arm here on the right of the torso. And similarly, a right arm here, artifact on the left side of the torso.